Again, welcome to Waidsum Academy. Today we're looking at nuclear physics, and in nuclear physics we'll be looking at the first part, which is the nuclear model of an atom. And in that nuclear model of an atom, we're going to look at the atom itself and the atomic structure. So before we continue, let's listen to this tutorial.
Hi there. Today we'll be looking at atomic structure. We'll start off by taking a look inside the atom. At the center of every atom, there is a small positive nucleus. This is orbited by negative electrons, which are grouped in shells. While this is the most commonly used model of the atom, it's important to remember that this is not what an atom actually looks like. Let's take a closer look inside the nucleus now. Inside, we have two types of subatomic particle: neutrally charged neutrons and positively charged protons. These positively charged protons give the nucleus its overall positive charge. If you're struggling to remember the relative charges of these two subatomic particles, the alliteration between their charge and names might help. Neutrons are neutrally charged, and protons are positively charged. Protons, neutrons, and electrons are all incredibly small. Their masses and charges are also very small. We describe the masses and charges relative to each other. That's to avoid writing 27 zeros each time if we were to use kilograms. You need to know the relative masses and charges for neutrons, protons, and electrons. Neutrons have no relative charge. Protons, which are positive, have a relative charge of positive 1, and electrons, which are negative, have a relative charge of negative 1. Neutrons and protons both have a relative mass of 1. The mass of an electron, however, is 2,000 times smaller than these. You won't need to know the relative mass of an electron in your exam, and you can just use the term negligible. This means it's so small that it's unimportant. In an atom, the number of protons and electrons are equal. We know this because atoms have an overall neutral charge. If this weren't the case, then every atom would repel each other, and everything you see around you wouldn't exist. Thankfully, that doesn't happen. We know that protons have a charge of positive 1, and that electrons have a charge of negative 1. So, for atoms to be neutral, the number of protons must equal the number of electrons, so their charges cancel out to 0. When the number of electrons is not equal to the number of protons, we call that atom an ion. In this video today we have covered that the nucleus is positive and contains protons and neutrons. Protons, neutrons, and electrons all have different relative masses and charges. You need to be able to recall these in an exam, apart from the relative mass of an electron, which we can describe as negligible. And finally, in a neutral atom, the number of protons is equal to the number of electrons. Don't forget to check out all our other fantastic...
Okay, so that's the tutorial. We looked at the structure of the atom. We said the atom is made up of a nucleus and electrons which revolve around the nucleus. We said the nucleus of the atom contains the protons and the neutrons. And we said the protons are positively charged while the neutrons have no charge. And then we said the electron that orbits around the nucleus is negatively charged. And we say in an atom the number of protons is equal to number of electrons. So number of protons are said to be equal to number of electrons. So on that note, we say atoms are electrically neutral. Atoms are said to be electrically neutral. Why? Because the number of protons equals to number of electrons. So still looking at the structure of the atom, we say they have relative masses and charges, that the proton has a mass of 1 and a charge of plus 1. And the neutron has no charge. Okay, but it has a mass of 1, while the electron it has a negatively charged of negative minus 1, and the mass is very negligible, very small. That means 1 all over 2,000. 2,000 times smaller than the mass of proton. So, or the mass of proton and the mass of electron, because they're same size, proton and neutron. The number of proton, and the mass of proton and number proton and the mass of neutron, they are same size. They are 1. Okay. So, but the electron is 1 all over 2,000, meaning 2,000 times smaller than the mass of the proton and the neutron. So that's the first part we've looked at. Still on the atomic structure, we say the atoms, they are the foundation of any matter. They are the foundation of a matter. Okay? It's just like you say cells are the building blocks of life. Atoms are the building blocks of all matter. Any matter that you know that exists, whether it's in the solid state, is in the liquid state, or is in a gaseous state. Is that okay? So we say they are small. Atoms are small. Okay? They are small with a radius of 1 times 10 to the power of raised to power -10. So that tells you how small an atom is, incredibly small. Okay, and undoubtedly small. So if the radius is, because this will be 0.00000000001, that's the radius meter. That's the radius of an atom, right? So it shows you an atom is incredibly and unbelievably small. Okay, so this is about, like you're saying, 100 million atoms could fit side by side across a thumbnail. So if you take a thumbnail, 100 million atoms will fit side by side with the size of a thumbnail. So you can imagine that atoms are relatively small. Atoms are relatively small. Is that okay? Atoms have a tiny, dense nucleus at the center, right? That nucleus that it has the protons and the neutrons. Has the protons and the neutrons inside the nucleus of the atom. So at the center of an atom, in reality, this is how atoms look in reality. Not like the circular case we showed before. That one was just for the sake of drawing easy study. So for the sake of easy study, we draw a small nucleus. We have a small nucleus with proton and neutron inside. This is the nucleus of an atom. Then we have the electron orbiting around the nucleus. We have the electrons, they move in orbit. They orbit around the nucleus, okay? We have the electron moving around the nucleus. We have the electron moving around it. These are shares. This is the second share, or the second energy level. This is the second share of the atom. So for easy understanding, for easy chemistry, we do this, or for easy physics, we do this. But in real life, this is not how they look. This is not how they look, okay? The atoms, they actually orbit like this, okay, in this manner, in this pattern. So this positively, you see the nucleus is positively charged. Why? Because the proton is positively charged. The neutron inside this nucleus do not have a charge. So the only charge that is here, is a positive charge. Okay, the only charge that is here is a positive charge. Okay. Okay, so now we say the electrons are orbiting around the nucleus of the atom. The electrons, see, they're negatively charged. They're called negative electron. They're orbiting around the nucleus in the different energy level, okay? In their different energy level. The electrons are orbiting around the nucleus. This is the reality, how it looks in real life. In real life, this is how it looks. But the circular one we've shown before is just theoretical. It's just theoretical. And we say the radius is about, or the diameter is about 10 to the power of negative 10 meters. Okay. Then we say that inside the nucleus you have a small positively charged proton, right? And then the neutron that are also in the nucleus do not have any charge. The neutrons do not have any charge. But the proton, because the protons are positively charged, the entire nucleus of the atom will be positively charged, because it is the only charge that is in the nucleus of the atom. It is the only charge that is in the nucleus of the atom. Right? Because the proton is the only charge that is in the nucleus of the atom. Hence, because the proton is the only charge that is in the nucleus of the atom, hence, we say the nucleus is positively charged. We say the nucleus is positively charged. Now let's take a look at some basic experiments that have been done by earlier scientists. A good example of those early scientists is Rutherford. A good example of those early scientists is Rutherford. Okay, Rutherford is one of those great scientists who was, I think, in the University of Manchester, who had two students, Hans Giger and Ernest Matzi. He had these two students that were working for him, and these two students were doing master's degree in the University of Manchester. I think somewhere around 1909, somewhere around there, 1909, okay, or somewhere around that time, okay. These guys, he had two. Rutherford was a great professor in the University of Manchester, and he had two students that were working, doing master degree on the nuclear physics, okay, on nuclear physics. So, and the experiment we're going to describe, we say in 1909, a group of scientists were investigating the plumb body model. Remember, the plumb body model had earlier be established, but these scientists, they were investigating this plumb body model, if it is to verify the authenticity of the plumb body model, to verify the authenticity of the plumb body model. Is that okay? Every time my screen goes to your ship. Okay, sorry, okay. Once the screen sleep, and then we have issues. We should be touching the screen. Okay, so these scientists, good example, physicists. You know, a physicist is a scientist. A chemist is a scientist. A biologist is a scientist. They are all scientists. We also have computer scientists. So science has various dimensions. So if you are a physicist, meaning you are someone who is a specialist in physics, who is a physics scientist. So a physicist, Ernest Rutherford, was instructing two of his students. Okay, I've already mentioned this. Two of his students, Hans Giger and Ernest Matzi. Okay, depending on how you pronounce it, okay, to carry out this experiment. Now, what was the experiment? The experiment has something to do with scattering the alpha particle, which is nuclear physics, which led to today's nuclear physics, was about scattering the alpha particles by a sheet of thin metal support and the nuclear model of the atom. So they were trying to bombard the alpha particle, to scatter the alpha particle, to hit an atom, and see whether it will be stopped, whether it will deflect, whether it will deflect, whether it will pass through the atom, whether it will, you know, they wanted to see what was going on. If you bombard an alpha particle, if you fire an alpha particle to pass through an atom, so what will happen? So this was what the experiment this master student were doing for their professor, Ernest Rutherford. Remember, Ernest Rutherford was a professor in the University of Manchester in somewhere around 80-something to 90-something. So this is two students, Hans Giger and Ernest Matzi. They were carrying out this bombardment in the lab, in the physics lab. They were carrying out this bombardment, firing an alpha particle towards a metaphor which is an atom, which represented the structure of an atom. Now, a beam of alpha particle, you know, alpha particle could be a helium nucleus, okay? Remember, we always write helium nucleus for alpha particle, right? Remember that. We always write helium nucleus for alpha particle. We always use helium nucleus for alpha particle. For example, alpha particle, you know, the symbol is like this. We write an alpha like this, but we write He, helium nucleus, to represent an alpha particle. And this nucleus, since it's helium, it has atomic number 2 and it has mass number 4. Okay, this is a symbol of alpha particle. This is an alpha particle. So they took a helium nucleus to represent an alpha particle, and they fired this helium nucleus towards a metaphor, and see whether there will be deflection, or the helium nucleus can go through it. This was what the experiment was about. Okay, they call it the thin gold foil. A thin gold, you know, gold is a metal, so that's sometimes we call it a metal foil, or you call it a thin gold foil. Okay, so the fire beam of alpha particle, that's a helium nucleus ion, the ion of a helium, and they directed this helium ion towards the thin gold foil. Now, what was expected? What were the observations? What did they see after they did that? They expected the alpha particles to travel through the gold foil, right? They expected the alpha particle to travel through the gold foil. They expected the alpha particle normally to go through the gold foils, because this is how they discover something else that we're going to talk about. And maybe the change direction, maybe change direction, maybe like small amounts, like change direction by small amount, like small bending. Okay, instead they discovered that this is what they discovered. What they expected is not what they saw. What they expected, these two scientists that were working with the professor, these two young master students that were working with the professor in the lab, what they discovered is what we're about to highlight. Now, they discovered that most of the alpha particle pass straight through the foil. Most of them, when they fire them, they could pass straight through. Okay, they discover, okay, let's take, this is the example, this is a thin gold foil with a nucleus here. Let's say this is the nucleus. This is the nucleus. Now, in the lab, they were firing alpha particle or alpha ion. Okay, in this case, we represent with helium ion like this, 2+. When you say 2+, means it loses its 2 electrons. So they fire these 2 electrons. So when they fire, it go through. Most of them will go through. If you fire this one now, because here is empty, it will go through, right? It will go through like this. So this Hans Giger and Marsden, they discover when they fire, most of them they go through. They go through the gold foil, the thin gold foil. They fire another one, probably it went through. They fire another one, it went through. Okay, assume this is a straight line. Okay, so they fire another one, it went through. This was the experiment they were doing in the lab. They fire another one, it went through. They fire another one, it went through. They fire few, only few of them were deflected. The one that hits here, maybe they deflected backward or sideways like this, or sideways like this. Only few of them were deflected. Only few of them were deflected. So, but most of them that they fire, they went through. Most of them they fire, they went through. They noticed that only somewhere in the center, the one that hits the center, they were the ones that were deflected. They were the ones that were deflected. Only the ones that hit the center or passes through the center, they were the ones that experienced deflection or that bounced off. But the one that were every other part of the atom, that were fired through every other part of the atom, went through, were never deflected. So this was the report they made. I say they reported to their master that most of the alpha particles that we passed through the foil, they went through. Most of the alpha particles they passed straight through the foil. This was one observation they wrote down. Another observation is that some of the alpha particles changed direction, but continued through the foil. Some changed direction, but they continued through the foil. They bend, like maybe they fire here, and then they went like this, they continue. Or they went down like this. That they went down like this, or they bent and went this way, or they bounced this way. So they changed direction. Some of them changed direction. They started to write down all their observation. That okay, some of the alpha particles they changed direction, but they continue through the foil. Then a few of the alpha particles bounced back off the gold foil. Few of them bounced back, like these ones. This one that bounced back. Okay, few of them bounced back, going back. Okay, so these 3 observations they made. Most of them passed through. Some of them changed direction. Some of them bounced back. Few of them bounced back. So they wrote down these 3 observations. They wrote down these 3 observations. And this is the analysis and the conclusion they brought up thereafter. They said instead they discovered, this was from the analysis and discovery establishment after several experiments. They discovered that most of the alpha particle, okay, we've already established these 3 points. Now, this was their bigger observation. Now, the bouncing back could not be explained by the plot body model. They said the plot body model could not explain the bounce back that they've experienced. Okay, this was one big thing. Could not be explained by plot body model, meaning there is need for a new discovery or a new addition to the body of knowledge. So, a new model was to be created. They have to create a new model as scientists. That the plot body model did not suffice for everything. So they have to create. Now, this was the first evidence of the structure of the atom. This was the first evidence of the structure of the atom, that the atom has a nucleus at the center. Now, every time the alpha particle hit the center, they bounce back. Okay? If they hit very close to it, they bend. And if farther away from the nucleus, the center, they just go through it. So they're able to see this firing. See a lot of firing they did. The ones that were very close to it, remember, they were repelled. You know why this is repelled? Because alpha particle, right? Alpha particle is positively charged. Meeting another positive, it will repel. So that's where this one was repelled. The one from the bottom also repelled that way this way. Few ones that hit exact center, the nucleus, where the nucleus was, they bounced back. But majority went through. Majority went through. So this was a new dawn. This was a new dawn. That when an alpha particle are fired at gold foil, most of them they go through, but a very small number they bounce back. They bounce straight back to where they came from. So this were the conclusion they had. Now when an alpha are fired at the pieces of the gold foil, the majority of them will go through. Yes, majority will go through. Because those ones you fire through the bottom here, below here a little bit will go through. The ones on top will go through. Unless the one very close but did not touch will bend. Will bend away. From the bottom will bend downwards. And the one that hit the nucleus we return back, we bounce back. So this was the complete observation that they've had. Okay, and they said this happens because the atom is mainly empty space. Majority of the part of the atom is an empty space. So they concluded, you see, all these are empty space except this center nucleus, the nucleus. So majority of the atom is an empty space. Majority of the atom is an empty space. That's why all this happen. That's why that when you fire the alpha through a gold foil, majority of them will go through it. Majority of the alpha particle will go through the gold foil structure of an atom. Now, some are deflected through a small angle, like these ones. Like these ones, deflected through a small angle. You fire this one, the ones very close to the nucleus, they're deflected through a small angle. And also this one. You fire this one, you see, they deflected through a small angle. So now here it was their conclusion. He said this happened because the positive alpha particle are repelled by the positive nucleus. You know, the alpha particle you are firing is a positive, is positive, and the nucleus is positive. So positive will repel positive because like charges will repel each other. So that's why some of them will be deflected at small angle. Those that are fired close to the center, the nucleus of the atom, they will be repelled at certain angle. The very small numbers are deflected straight back. Small numbers are deflected. Why? This is because the nucleus is extremely small. The nucleus is very, very small. Now let's take a look at the atoms and ions. Let's take a look at the atoms and ions. An ion is electrically charged atom. You know, when atom lose electron or gain electron, it becomes an ion. When atom lose electron or gain electron, it becomes an ion. For example, if you say sodium atom, Okay, elements are regarded as atom. Okay, if you take a sodium atom, you know it has atomic number 11, right? Which is 2. If you draw the electronic configuration, you have 281. Your electronic configuration, you have 281. 281, meaning it has 1 electron in the outermost shell. So it can only give out 1 electron, right? So that's why we write plus 1. You know, we don't write, no need to write plus 1. Plus 1 is same as just plus. Okay, just same as just writing plus. It's just like you say 1 orange. It's better you just say orange and orange. Okay, instead of saying 1 orange. It's the same thing. Okay, so sodium has plus 1 because it's going to give out two electrons. It's going to donate 2 electrons. Magnesium has 2 plus because it's going to donate 2 electrons in the atmosphere. The 2 electrons it has in its atmosphere is going to donate it because magnesium is 2, 8. First share we have 2. Second share we have maximum number of electrons, which is 8, and the third share we have 2. It is the number of electrons you have in your atmosphere that you can either give or add to. Those who give, they become positively charged. Why are they positively charged? Because when you give electron out, you now have, you know, both electrons and protons are same 11 for sodium. Proton is 11, electron is 11. So why is it positively charged? Why is it this ion positively charged? Sorry, 11. Now, if you give 1 electron, it becomes minus 1. If you minus 1, there will be 10 electrons. There will be 10 electrons for sodium, but there are still 11 protons. There are more protons now with 1 addition, with 1. So 11 is more than 10 with 1. That's why it has 1 plus. So when you give, because it has given 1 electron to maybe chlorine, so that it can form sodium chloride, ionic bonding. Okay, so that it can form sodium chloride in the process of ionic bonding. Okay, so this is why this one becomes positively charged. So when you lose electron, when an atom loses electron, it will become an ion. It's not only when you give out, also when you receive, like chlorine. In the case of chlorine is just raised to power minus. When you receive electron, you become negatively charged. Why are you negative? Chlorine is 17. Atomic number is 17. Since atomic number is 17, the electronic configuration is 287. 287. Okay, 287. Meaning chlorine, you know, if you have 8, you become stable. Okay, the maximum number of electron atoms hold in any shell is 8, the maximum. So this one is looking for 1. Chlorine is looking for 1 electron to make 8, so that it becomes stable, 288. Okay, so it gets down 1 from sodium. You know, sodium is giving, so you can get from sodium. When you receive, you become negative because you now have more electrons. Your electron will no longer, you know, your number of protons is 17. If you receive 1 electron will now be 18. Electron will be 18. So electrons are now more. The negative charge are now more than the positive. That's why it becomes chlorine minus. So atoms that receive electrons, they become negatively charged because their electron will be more than their protons. The number of electrons will be more than the number of protons. They become ions. So the point we are explaining here is that when atoms lose electron or gain electron, they become ions. Ions are the ones you write, you put the plus or minus on it. Okay? Atoms, you don't put plus or minus. So ions are atoms that have gained or lost electrons. Atoms that have gained electrons or atoms that have lost electrons, we call them ion. A stable atom is normally electrically neutral. For any atom that has not lost electron or gained electron, we say that they are electrically neutral. Why? Because the number of protons is always equal to the number of electrons. The number of protons are always equal to the number of electrons. Okay, so positive ions are therefore formed when atoms lose electrons. We've explained this. Positive ions are formed when atoms they lose electron, like sodium. When sodium loses 1 electron, it becomes positive, Na plus. When chlorine gain electron, it becomes negative. So negative ions are formed when atoms they gain electrons. So we've already established this. You know how to draw the atomic structure. The atom is neutral when the number of protons is same as the number of electrons. An atom is said to be neutral when the number of protons is said to be number of electrons. For example, let's take a look at this. Okay, this carbon atom, right? Now you can see that the number of protons is 6, number of neutrons is 6, number of electrons is 6. So this atom is neutral. Now this atom is negatively charged. Why is it negatively charged? Because it has more electrons. It has gained one electron. It has gained one electron is now more than proton. Number of electrons is now more than number of proton. Once your number of electrons is more than your number of proton, you become negatively charged. You're going to be minus. You're going to have a small minus on top. If you gain 1, it will be 1 minus. You gain 2, it will be 2 minus. If here is 8, it will be 2 minus. If here is 9, it will be 3 minus, depending on the number of electrons you gain. Is that okay? Then this one, you see, electron is less. It has lost electron. This atom is going to be positive charge. It's going to be positive. Whatever you write, you're going to write positive on top because it has lost 1 electron. There are more protons now than electron. Is that okay? So, I think, let's see if we're going to have a next section. The nucleus. Okay, let's listen to this tutorial about the nucleus before we move to the next section. Let's listen to this tutorial about the nucleus before we move to the next section. Now, the first tutorial.
Hi, this video is all about atomic and mass numbers. We'll start off with nuclides. A nuclide is a type of atom with a set number of protons and neutrons. The atoms shown here both have 3 protons and 4 neutrons. This means they're the same nuclide. Next up is proton number. Now this quantity is nice and self-explanatory. It tells us the number of protons in a nucleus. This atom of barium here has 4 protons in its nucleus. This means its proton number is 4. Simple, right? The proton number is also called the atomic number. Because protons have a charge of 1, the proton number also tells us the charge on the nucleus. Looking at this barium nucleus, the nucleus has a charge of 4, which is also the proton number. Okay, nucleon number, another friendly one. A nucleon is just a particle in a nucleus. That's protons or neutrons. Nucleon number, therefore, is the number of nucleons inside the nucleus. Both protons and neutrons have a relative mass of 1, so nucleon number is equal to the relative mass of the nucleus. This is why the nucleon number is also called the mass number. In the diagram on the screen, the nucleon number is 9. There are 4 protons and 5 neutrons. That's 9 nucleons. The nucleus therefore has a relative mass of 9 as well. Nuclide notation is a way of showing a nucleus's chemical symbol, which is represented with an X, the number of protons, which is represented with a Z, and the number of nucleons, which is represented with an A. As nucleon number is the number of protons and neutrons, we can calculate the number of neutrons in the nucleus by subtracting the proton number from the nucleon number. For sodium here, the nucleon number is 23, the proton number is 11, so there are 12 neutrons. We can't always rely on the nucleon number being at the top. Some sources may write them the other way around. The nucleon number is always the larger one for all nuclei except for hydrogen, where they're equal, and that's because it only contains 1 proton. An atom of aluminium, Al, has 13 electrons and 14 neutrons. Write down aluminium's nuclide notation. So, this question is worth 3 marks. We'll start off by finding the number of protons. This is equal to the number of electrons, which we've been given. We have 13 protons. Our proton number Z is therefore 13. This gains the first mark. Next up, we need the nucleon number in order to write aluminium's nuclide notation. This is the sum of the number of protons and neutrons, which are 13 and 14 respectively. Nucleon number A is 27. This gives us the second mark. Finally, we need to write it out in the proper format. Nucleon number is typically at the top left of the chemical symbol, which was given in the question as Al, and proton number is given at the bottom left. This is the final mark. Now, the number of neutrons is not included in an atom's nuclide notation. You won't get away with just sticking the two numbers from the question in front of aluminium's chemical symbol. There's some calculation required. In this video, we have explained that proton number is the number of protons, nucleon number is the number of particles in the nucleus, which is protons and neutrons. Nuclide notation tells us the chemical symbol, proton number, and nucleon number. And finally, to find the number of neutrons in an atom from nuclide notation, we find the difference between A and Z. Don't forget to check out.
Okay, so this part we've looked at the nucleus itself, the nuclide, we call it the nuclide, where we talk about the proton number, which is the number of protons, or the atomic number, the number of protons that are found in the nucleus of the atom, or which we also call the atomic number. We talk about the nucleon number, which is the sum of the number of protons or the sum of the particles in the nucleus. When we say nucleon number, is the particles, sum of the particles in the nucleus, which includes the number of protons plus the number of neutrons. Okay? Then, and this nucleon number is also called the mass number. It's also called the mass number, and we've looked at an example. So let's begin to take a look at the structure of the atom made up, what is made up of. The positively charged nucleus at the center is made up of what? Both the protons and the neutrons. Both the protons and the neutrons. So how you know which one is the proton here? You look at the electron, there are 3. So look at the one that is 3 as well, is the proton. Electrons here are 3, 1, 2, 3. So because number of protons is same as number of electrons, hence this red one that is 3 is the proton. The one, this green one that is 4 will be neutron, because proton and electrons, they are equal number. Okay, so for an atom that you are not told which one is proton, which one is a neutron. Is that okay? So this is the electrons are the ones that revolve around the nucleus. This is the nucleus, this place where you have the proton and the neutrons. Is the nucleus of the atom, and it's called the nuclide. It's called the nuclide. The nuclide, it consists of the particles that are found inside it, which are the protons and the neutrons. Which are the protons and the neutrons. Okay? So we always have a chemical symbol to represent this. And when we write the chemical symbol, we put the proton number, which is the number of protons in the nucleus, and the mass number, which on top, which is the nuclear number, which we call also called the nuclear number. Okay? So let's take a look at another tutorial and see what it has for us.
Here's a question for us to look at. So let's start by reading through the text in the question and then answering the question. A nucleus of helium has the symbol He32. Complete the diagram to show an atom of helium using P for protons, N for neutrons, and E for electrons. And we haven't been given any clues because it could be one proton or many, one neutron or many, and one electron or many. So let's just highlight what we have to do here. So we just have to complete the diagram. So we've got these positions here, and we need to fill these with P's for protons, N's for neutrons, and E's for electrons. So as a starting point, let's just remind ourselves of a model of the atom. This is often referred to as the Bohr model of the atom, after the scientist Niels Bohr. But we've got protons and neutrons in red and green, as shown there, and they make up the nucleus. And then we have these much smaller and very much lighter electrons, and they are to be found around the nucleus, relatively far away from the nucleus, and notionally we say that they are orbiting the nucleus. So we can start, I think, with the electrons. That's probably a good place to start because it's quite clear where they are. So let's go for it. So the electrons are located, and I've put orbits in inverted commas there because it's not quite as simple as that. But for the purposes of this course, we will just say that they're in orbits around the nucleus. So in the case of helium, we've got the 2 electrons there and there. The next part is the neutrons and the protons, and that means we need to understand what these numbers here, so the 3, 2 with the He for helium, what does the 3 mean and what does the 2 mean? So just as a reminder of that particular piece of the theory is, and this is the example of lithium, the number at the top is called the nucleon number, and the number at the bottom is called the proton number. So let's focus on the proton number. So lithium, the proton number is 3. We're not worried about lithium, we're worried about helium, and the number at the bottom is 2, which means that we know that the proton number for helium is 2, which means there has to be 2 protons in the nucleus. So we can go and fill those in. The number at the top is called the nucleon number, and the nucleon number is the total number of protons and neutrons in the nucleus. So we've got 3 particles in the nucleus, that's what the 3 over there stands for. 2 of them are protons, so the last one has to be the neutron. So that's the complete picture of an atom of helium.
Okay, so that's the example there that has been given and described. Now we remember we use some symbols to describe the nucleus. We say the proton number is Z. We use Z to represent the proton number. Okay, for example, if we take a chemical symbol, we take this X as our chemical symbol, Z will be our proton number. This Z will be our proton number, right? This will be our proton number. And normally we use A for our, we use A for our nucleon number or mass number. So when we're looking for the number of number of neutron, we say number of neutron is the mass number or the nucleon number, which is A, minus the proton number, which is Z. Minus the proton number, which is Z. So anytime we're looking for the number of neutrons, the neutrons plus the protons, they make up the nucleus. So anytime we're looking for the neutron, we say the mass number or the nucleon number minus the proton number. Then we can get the number of neutrons. Okay, so let's move fast for time's sake. Okay, so we say that the number of protons in an atom is called the proton number. And it's also called the atomic number. The number of protons is called the proton number or the atomic number. Okay? Elements in the periodic table, they ordered by the atomic number. They are arranged according to their atomic number. Elements in the periodic table are arranged according to their atomic number. Is that okay? So a good number of protons determine which element an atom is. A good number of protons. The number of protons determines which element an atom is. Okay, if the number of protons is 10, then the atom is neon. If the number of protons is 11, the atom is sodium. If the number of protons is 12, the atom is magnesium, according to the periodic table. Okay, so if the number of protons is 1, the atom is hydrogen. Okay, so this is how we name them. And they are singularly arranged. They are singularly arranged in the periodic table. They are singularly arranged in the periodic table. They are arranged according to their proton number, which we call their atomic number. They are arranged according to their proton number, which we call we say the atoms in the periodic tables are arranged according to the proton number. Is that okay? Now let's take a look at this one. You say, for example, hydrogen has atomic number of 1. So it always has just 1 proton. Since it has atomic number 1, so it has 1 proton. Sodium has atomic number 11, so it has 11 protons. Uranium has atomic number 92, therefore it has 92 protons. Okay, the atomic number is the number of protons. Is that okay? Same thing. The atomic number is equal to the number of electrons also, because number of protons is said to be equal to the number of electrons. Now, nucleon number, A, or the mass number. The nucleon number or the mass number is the total number of particles in the nucleus of the atom. The total number of particles. So when we say nucleon number, you are saying the total number of particles in the atom, in the nucleus of the atom. So which includes, what are those things in the nucleus? We have the proton and the neutrons. So which means the sum of the protons and the neutrons equal to the nuclear number. Now the number of neutrons can be found by subtracting the atomic number from the mass number, which is the formula I wrote just now. Number of neutrons is equals to the nuclear number minus the proton number, which means A minus Z, which means A minus Z. Is that okay? So let's go to nuclear notation. I've also demonstrated this. In the nuclear notation, this is the chemical symbol for elements. We use X just to represent elements. And then this one is the proton number, Z, or the atomic number. While this A is the nuclear number or the mass number. The nuclear number or the mass number. Now, the top number A represents the nuclear number, which I've already explained. All of this I've already explained. Now, let's take a look at a specific example. Okay, this is a lithium. For lithium, we have 3 at the bottom, 7 on top. Okay, sometimes they flip this. The 7 will be at the bottom, the 3 will be at the top. It's not always in this case. Sometimes they flip it. But what is to note is that the greater number is the mass number. The nuclear number is always the bigger number. Whether it's at the bottom or it's at the top. Okay, it doesn't matter. Whether this is at the bottom or the 7 is at the top or it's at the bottom, it doesn't matter. What I'm trying to say is, in some cases, this is written like this. You see this lithium that we've written like this, 3, 7. In some cases, it's not all the time that in some text it's written like this. Sometimes you see it like this. You don't get confused which one is the proton number, which one is in some text it's like this. In some text it's like this. Okay, but it doesn't matter in this case. What we are saying, the bigger one is the mass number or the nuclear number, while the small one is the number of proton, is the proton number. Is that okay? So that's the point we are making here. Now let's move on. We already know that the number of proton, or the proton number, is the atomic number, and it's also equal to the number of electrons. Also equal to the number of electrons that orbit around the atoms. Okay? Now let's take a look at this. Let's do some example. Let's do some revision as fast as we can. So this is this element symbol for gold. This is gold, AU. AU is gold, right? And the atomic number, the proton number is 79, and then mass number, the nuclear number is 197. Now we're going to fill some questions. Say, now how many protons, neutrons, and electrons are in this gold atom? Okay, are in this gold atom. So for gold atom, the proton number is 79. Number of protons is 79. So 197 minus 79, what do we get? To get the neutron. 197 minus 79, what do we get? The proton is this one for this. The proton number is this, right? The neutron is what? Okay, the neutron is 118, right? Oh, sorry, the neutron is 118, this one. So we choose the neutron here, 118 for gold. Then the third one is the electron. Electron will be what? 79, right? Because number of electrons is same as number of protons. So electron will be 79. Right? Electron will be, for electron, this one will be D, right? Right? For neutron, it's C. The answer is C, this one, which is 118. For proton is what? 79, right? Okay. So that's it. The number of proton is 79. Number of electrons is 118, and the number of neutrons is 118. Number of electrons is 79 as well. Okay, so that's that for that. Say the answer is D. Okay, it's A, B, C, D. So this is A, this is B, this is C. Which one is correct? Which one has a proton 79? D, right? It has electron 118, and it has it has neutron 118, and it has electron 79. Is D. So the correct answer. So you can see something like this in the exam. in multiple choice in the exam. So the symbol for gold, you say the element symbol for gold is AU. How many protons, neutrons, and electrons are in gold atom? So they give you something like this, and they give you this option A, B, C, D. So the right answer is D, because it has 79 protons, 118 neutrons, and 79 electrons. So the right answer is D. Now the gold atom has atomic number 79, and the mass number 197, okay, which is on the top, okay, from the chemical symbol. From the chemical symbol, 197 is the mass or nucleon number, and this is the atomic number or the proton number. 79 is the atomic number or the proton number. Is that okay? So that's that for this question. And then before we call it a day, let's take a look at isotopes. And let's listen to this tutorial for isotope briefly. Okay? Let's listen to this tutorial for isotope.
In this video, we're going to cover isotopes. To define an isotope, we first need to remind ourselves of the definition of an element. An element is defined by its number of protons, so all the atoms of an element have the same number of protons. The number of neutrons, however, can vary. Isotopes are versions of the same element with different numbers of neutrons. These atoms are both lithium atoms, but they have different numbers of neutrons. These are isotopes. This means that isotopes have the same proton numbers, but different nucleon numbers. The first isotope has a nucleon number of 7, while the second isotope has a nucleon number of 6. Both have a proton number of 3, as they are both isotopes of the element lithium. Isotopes are given different names to help distinguish between them. These names are based on their nucleon numbers. This first atom is called lithium-7 because it's an isotope of lithium and it has a nucleon number of 7. The second has a nucleon number of 6 and is therefore lithium-6. You may notice that their electron structures are identical. Isotopes of an element have the exact same chemical properties, which is how they behave in reactions, because the arrangement of their charged particles is identical. Exam questions on isotopes come in a wide variety. Here's one example. Thorium-230 has the nuclide notation 230-90Th. Calculate the number of neutrons in thorium-232 for 2 marks. First, let's calculate the number of neutrons in thorium-230. The number of neutrons is the difference between the nucleon number and the proton number. This is 140. Identifying this is the first mark. Next, we'll look at the difference between thorium-230 and thorium-232. There is a mass difference of 2. Thorium-232 must have 2 more neutrons than thorium-230, as they are the same element and therefore have the same number of protons. This tells us that thorium-232 has 142 neutrons, which is the second and final mark. As is often the case, there are multiple ways to go about this. Let's take a look at another method for the same question. If your first instinct was to find the number of protons in thorium-232, this is the method for you. By spotting that thorium-230 and thorium-232 are isotopes of the same element, we can deduce they have the same number of protons. So thorium-232 has 90 protons as well. That gains the first mark. We know that there are 232 protons and neutrons in the nucleus of thorium-232. So, to find the number of neutrons in thorium-232, subtract 90 from 232, which leaves 142 neutrons. This is the second mark. This video explained that isotopes are different versions of an element which have different numbers of neutrons. We name isotopes by the relative mass of their nuclei, and isotopes of the same element behave almost identically in chemical reactions, thanks to having identical arrangements of charged particles. Don't forget to check out all our other fantastic revisions.
Okay, so this part explains about isotopes. That isotope of an element, they have the same number of what? They have the same number of protons but different mass number. And hence, because they have different mass number or different nuclear number, hence they have what we call different number of neutrons. Their neutrons are different because their masses are different. It's just a different version of the element. Isotopes are different version of the same element. Okay, so we've taken a look at that. So we say although the number of protons in a particular element is always the same, the number of neutrons can be different. When the number of neutrons are different, we say the element, that same element with different neutrons exists in isotopic nature. So isotope are atoms of the same element that have an equal number of protons but different number of neutrons. Hence we can say isotopes are elements with the same chemical formula. Because they have the same number of protons, hence they will have the same number of electrons. So isotopes are elements that have the same chemical formula but different physical formula or different physical concept. We can put it in that manner. Isotope tends to be more unstable due to their imbalance of the protons and the neutrons. The imbalance that exists between their protons and neutrons makes isotope to be a bit unstable, especially radioactive elements. Okay, this instability is called radioactivity, which we're going to look at. That means they will disintegrate. This kind of elements that are unstable will disintegrate under intense condition. Now, this means that they are more likely to decay. That's the meaning of disintegrate. When I use the word disintegrate, means they are more likely to decay because they become unstable. When you are unstable, you can decay or you can disintegrate. And this happens to isotopes. Because they are unstable, likely unstable because of the imbalance in their protons and neutrons, hence they are likely to decay. And as such, they emit particles like alpha particle, beta particle, and gamma rays, which we're going to talk about under radioactivity. Okay, so we already know how to represent protons, neutron, and electron. We already showed that characteristics. Now you can see hydrogen exists in three different states. The first one proton number is 1 and mass is 1. This one is called the hydrogen atom. Now when you have one proton and mass number or nucleon number 2, this is called deuterium. Hydrogen in three different isotopic nature. Okay, hydrogen, deuterium, and tritium. Tritium is the hydrogen with 1 proton number and 3 mass number. This is called tritium. So you need to know that hydrogen itself exists in three different isotopic nature. The H11, H12, and H13, which is called hydrogen, deuterium, and tritium. Is that okay? So different elements have different isotopic nature. For example, chlorine. Okay, this is a question for us to look at. Which of the following elements are isotope of each other? Which ones are isotope of each other? Now, remember, for an element to be an isotope, it must have the same number of protons. So this A is wrong because the number of protons is 17 for this isotope and is 18 for the other one. So it's wrong. They must have the same number of protons, but different mass number or different nuclear number. So this one is wrong. A is wrong. B, let's take a look at B. 92, 235, and 238. So B looks correct. B is correct because they have the same number of protons, but different mass number or different nuclear number. Now let's take a look at C. C is wrong because the protons are not even the same, and D is wrong because the protons are not the same. So the correct answer you can find in multiple choice exam is B because they have the same number of protons and different nuclear number or different mass number. Okay, the correct answer is B. Okay, so I think for this we will be stopping here for today, right? We're stopping at, let's say, where we are. We're still in 1.2. I think the next one will be proton, neutron, electron, right? So with this, we've come to the end of our class today.